Okay, so then today's topic again is multiple linear regression. So getting back to like linear regression, just to get the basics. So linear regression is an old and basic regression algorithm, but due to its simplicity, it is still one of the most commonly used statistical or machine learning algorithms. So to demonstrate today, we're going to use the data, like employee data, and each row represent each employee. And then it has a various variables or columns, if you will, about to describe each employee. And then like we are interested in this monthly income. Basically, like we want to understand like how this monthly income get decided, what makes a difference among the employees. So just to refresh the linear regression basics, we talked about linear regression in the previous seminar. But so just imagine like we have the monthly income, but then like let's say like we want to see like how the working years, how many years you work in this organization, impact on the monthly income or influence the monthly income increase or decrease kind of stuff. So like we have the two variables, and then like we basically mapped out all the employees by using those two dimensions. And then we want to find a simple pattern that can explain both the given data and the data we don't even have at hand right now. So to do, the simple way to do it is you draw the line, the straight line that makes sure that line and then each data, in this case, the employee, the distance to be minimum. So like it usually goes kind of like a middle of all the data points. And then that blue line is the model. How you describe that model? Well, that's basically like you need two things. One is a slope, another one is a y-intercept. In this case, let's say like we get this formula. This formula itself is the linear regression model. Slope is 500. Here is like, it's basically like 1 point increase on the x-axis, how much increase on the y-axis. That's the slope. And then the y-intercept, in this case, 5,000. 5,000 is the value on the y-axis when the x value is 0. So basically, linear regression algorithms find these parameters based on the given data. So in exploratory, let's just go quickly back to the exploratory. So here's a data, here's a summary view, and then basically here's a table view. Each row represent each employee. And then like, we are interested in this like monthly income this time. So let's go to the analytics and then select the linear regression. And the target variable is the monthly income. And then predictor, like or explainer variable is the monthly income, working years, total working years. And then click run. And then we built the model behind the scene, and it shows the visual chart error bar. Here we can see the coefficient 467. That's the slope. And if you go to the coefficient table, here is a coefficient 467. That this value was visualized in the coefficient tab. And the y-intercept 1,227. So if you don't even work, you just start up at this organization, your salary is going to be like 1,227, basically, without any other variable influence. So get back to the slide. But here's a problem. So there are some variables correlated in this data. For example, the working years and age, as you would imagine, they are very correlated. And there are other variables as well. And then that becomes a problem because that means one variable, for example, something like working years increase or the decrease, then like another variable also gets increase or decrease because that's what correlation is about. So that makes kind of hard to understand the independent effect influence of the working years. So the question is, how can we know the independent effect that is coming from just working years? And that means, so we have this kind of formula, the monthly income equal 500. This 500, 5,000, these two values are different from what we saw in exploratory, but I'm just making up these numbers to explain this thing simply. So 500 multiply working years plus 5,000, right? So then let's find what are the other variables that are correlated to working years. So go back to the exploratory and then let's create a new analytics and then select the correlation by columns and then variable columns. This here, basically like you can select all the numerical variables, then find the correlation for every single pair. So for example, this total working years is correlated with age about like 0.68. That's a correlation value. And then another one here, this seems to be higher. It's like 78, right? 0.78, that's higher. By the way, like a 1 is the highest and then 0 is the lowest. And then like -1 is also highest, but in the negative direction. So like one value increase and the other value decrease. So, and here, total working years and monthly income is also correlated. So looks like this total working years is correlated with these three variables. Let's take a look at with this job level. So go to the chart. Typically, like if you want to understand what's that 0.77, whatever the correlation value means, you, in this case, a numerical and numerical, we are comparing these two numerical variables. And typically you use a scatter chart. Then let's see, job level on the x-axis, and then like working years here. Then like we get something like this. The problem of this though is that like when you have like less values on the x or y axis either way, and then what happens is there are a bunch of dots can be on top of each other in this case. So it looks like in the job level, we have only 1, 2, 3, 4, 5. And then even though this is a numerical variable, but it looks like category. So in that case, when you want to compare, understand the relationship between a categorical variable and a numerical variable, box plot or violin chart usually is a good option. So let's try that. So here, I'm going to try the box plot. And then we get something like this. And then right now, the default is kind of a categorized numerical variable get categorized, but we don't need that. We want to show the original number. So like 1, 2, 3, 4, 5. So the job level and the working years are, we can see like some correlation here. So when the job level increase and the working years increase, or working years increase and the job level increase. So that's what's happening here. So these two variables are correlated. So that means that if you draw some kind of like a diagram, it becomes something like this, right? So like working years and then like a job level and a monthly income, and then job level to working years, they're correlated just like we saw. So that means the working years increase and the job level increases too. So that means that maybe it's not because the working years increase and the monthly income increases. It's just that like a job level increases and then the monthly income increases. So we saw the relationship between working years and monthly income might not be the causal relationship. It might be something, it's more like to do with the job level if you want to find out if the monthly income increase or decrease. Or maybe, you know what, like maybe the job level is not actually the one, it's actually the working years is a deciding factor for the monthly income. We don't know. Or maybe both job level and the working years, both of them have effect on the monthly income. So maybe some part coming from job level, and even within the job level, maybe like working years, longer working years might give you the higher monthly income. We don't know, but we can think about like multiple scenario here. So if we just investigate, just forget about the model, like how we want to do that, how we want to find basically how one additional year of working years has an effect on the monthly income. Simple way is just compare the two groups of people. So like the two group of employees. So like one is 10 years, another one 11 years. These two group difference is like 1 year difference. Right? And then like, we can get like average of the monthly salary of each group. Then like 8,000, 10,000. So there are 2,000 difference. So that's the difference coming from working years. Well, here's a problem, right? So like that's because in two groups, each group has an employee with various job levels. We didn't control that part. So what that means is we have the two groups, 11 years group and a 10 years group. And within that, like the various job levels. And when you look closely, in the 11 years group has more purple people or orange people, while 10 years group has more green people. What is the green? Green is a level 1, and then the orange and purple is a level 2 and level 3. So that means the average of 10 years and the average of 11 years, the difference between these two groups might be coming from the job level, not because of the 1 year increase. So how can we see the effect of just working years alone? Well, it's actually simple, right? So if we can control the job level, meaning we pick only the people with the job level 1, and then we basically create the two groups of like 10 years working folks and 11 years working folks. That means like only the difference between these two are the working years. Forget that like all the other variables might be different. How about the gender? How about like the location? How about the education? Yes, those are the important things. But let's simplify here just to focus on only two variables, working years and job level. And as long as we talk about those two variables, we can say from here, the only difference here is only the working years. And then we get the monthly income average of each group, and then like 8,000 and 8,500. The difference is $500. So then we can say this $500 differences must be coming from, or most likely it's coming from this working years, or at least not from job level. So what we have just done is basically like let's go back to the original diagram. We have this problem, like which one is influencing the monthly income. And what we just did was basically we hold one variable to be constant, right? So in this case, let's say like if we, I think what we did was something like this here. So we hold job level to be constant, to be just 1. It doesn't have to be 1, can be just 2 or 3, but just hold it constant. And change only the working years from 10 to 11 or 11 to 12 or whatever. And then that case, and if we see some like a difference in the monthly income. And we can do the opposite way. So for example, we can hold working years constant. Let's say like just keep it only 10 years folks or like 11 years folks, just to keep 1 year group. And then within that, like we can see like we can compare the people with job level 1, job level 2, or job level 2 and job level 3 and so on. And then see if there's any effect on the monthly income or any changes in the monthly income. So actually so now that we know that some kind of like how we go about this to address this problem, well, that's where the multiple linear regression can help us. So the 4 things I want to talk about. So the first is the interpretation of the multiple linear regression, and then like later on, like I want to get into more like variable importance, variable selection, and also building multiple linear regression models. So let's start with interpretation. So let's revisit the interpretation of coefficient. Forget about the multiple regression. Let's focus on simple regression again. Just I want to make sure everybody on the same page. So we get this formula, right? This is linear regression form, simple linear regression formula. Y equal A multiplied X plus B. A is a coefficient, and X is the predictor variable. So that to interpret this, like we can say 1 point increase in X would expect a change of A in Y. So what the hell am I talking about here? So let's use the real world data example. So we can rewrite this formula to be like monthly income equal 500 multiplied working years plus 5,000. So that means when we interpret this, 1 year increase in working years would expect $500 increase in monthly income. So, so that means, so that's a simple linear regression. So now if we extend this to multiple linear regression. Multiple linear regression is all about multiple variables, predictor variables. So instead of just x, and we added like x2. So like now we have like x1 and x2, and each of the variables should have its own coefficient a1 and a2. So then to interpret this, like, it goes like this: 1 point increase in x would expect a change of a in y when all the other variables stay the same. In this case, we have only 2 variables. So that means when I said other variables means only x2. And then like, let's use a real world example here. It's like monthly income equal 500 multiply working years plus 600 multiply job level. I just added a job level here, and plus 5,000. And then interpret this like base equals 1 year increase in working years would expect $500 increase in monthly income. This part is exactly the same as the simple linear regression. And then here's a new thing: the job level stays the same. This is the part that like I was talking about to hold the other variable constant part. So let's unpack it, what that means. So if you work just for 1 year, so let's say like working year is 1 and the job level 1, and then that put these numbers into the formula or this linear regression model, we get 600 is a monthly income, because 500 multiply 1 plus 600 multiply 1 plus 5,000, right? But let's say like if you work just for 2 years, but stay at the same job level, then what happens is, well, like you put a 2 in, instead into this working years. So then the calculation becomes 500 multiplied 2 plus 600 multiplied 1 plus 5,000. That becomes 6,600. So when you compare these 2 numbers of like 1 is working years 1, the other working years 2, but the other variable, in this case, the job level stays the same as the 1. Right. Then like we get like 6,100 and 6,600. So basically $500 increase. And this $500 increase is coming from that coefficient of the working years variable. So go back to the original like pictures, like we have 1 year and 2 years, and then 6,100 and 6,600, and then that increase is the coefficient. And then interpret this 1 point increase in x, we would expect a change of a in y when all other variables stay the same. So this part, so like basically, it's almost like 2 sentences to understand multiple linear regression. Rarely, like you're gonna go with just one variable. So like most likely, like more often than not, you end up like having a multiple linear regression anyway. So like it's like and then to interpret the coefficient, it's always there 2 sentences. And then this second sentence, sometimes it's kind of hard to remember, like when you starting out, because all you care, like all of us care, is like how much of the impact of this variable. But then make sure to always state this like when all other variables stay the same, piece, because that's the part helps you to even explain the independent coefficient of the given variable. So let's see. So working years and job levels, and let's take a look at how that thing out. So just one sec. Okay, here let's go back to exploratory, get back in the analytics, and then go back to the linear regression model we created. So before, like we had this only total working years. Now, how about like we have only total working years as a predictor? If we add the job level, and then click OK, and then run, and it creates the model. And then if we get 2 variables, let's go to the coefficients tab, and then we have the job level, and which is like a coefficient of 3,788, and the total working years is like 46. And that's what we get. And then here is though, like, so both of them are significant because the p-value is this, like, for example, this case, 4.3428, blah, blah, blah. And then like at the end, E-9. E-9 means 0.1. like or like you say 9 times, right? So like 0.0000434. So it's basically very close to zero or getting closer to zero. So it's pretty small number. So like there's something that like happening without almost like impossible to happen without using total working years to explain this change in the monthly income. So both of them have something to do with monthly income's change. Okay. Then with that information, we can draw the formula like this, right? Like so monthly income equal and this formula. And then in order to understand 1 year increase of working years, would expect $46 increase in monthly income if job level stays the same. Notice though, this now we have only $46 difference. So before, of course, if we didn't have this job level, and then if we run it, and then here is the influence is like 467. It's almost like 10 times bigger. And that's because this 467 probably not coming from not only coming from total working years, but probably coming from the job level. But job level influence was just kind of embedded in this total working years. That's why you see bigger number here. But the moment you add the job level, then like that number decrease because now the job level influence is coming from here, and then the total working years only influence effect is coming from here. It's 46. Again, we have only 2 variables here. Like we have other like there's 28 columns, so there are more variables here. But I'm just trying to explain by using very simple case. We're gonna start developing more variables after this. So. So both working years and job level have effect on monthly income, at least, and then like there's some differences, but it still have an impact. So now, let's get into the variable importance. What is that? So let's include all the variables. We just kind of go those 2 variables, but hey, we have more variables, so let's include all of them. So from age to monthly income, we don't need this category thing. We could up to work-life balance and okay, and then generate, and then like we get something like this. Okay, so we have like job levels here, and then total working years here, and then there are other stuff like a job role manager, the director, and job role technician, and so on. So the red means a decrease. So like, and then these are the categorical. And in order to understand the category and interpret the coefficient of categorical variable, you have to know what is the base level. So base level of job role is sales executive. So compared to sales executive, if you're a manager, you can expect this much in average. So like $4,000 increase in average. But if you, let's say here, laboratory technician, when you compare to sales executive, you get $721 decrease. When you see something like this, you can't help. I mean, like I can't help comparing to the next variable, so like side to side. So like these 2 like jump into my eyes, and therefore, oh, looks like a job role is more important than job level. And then when you look at something like here is closer to 0, this is like a total working years, it seems like there's not much effect. Therefore, probably we can ignore something. That's actually not the right thing to do. You don't want to compare side by side. This is really purely like you want to focus on just one variable at a time. Why I'm saying this is because what we're sort of like naturally doing is trying to understand which variables are more important than the others, right? And then but the higher coefficient doesn't mean more important, and because the units are different. What that mean? Well, oops, there's some kind of like a formatting problem here, but 1 unit in year means 1 year, and 1 unit in job level is 1 level. The 1 unit in job role is the difference between the sales executive and the sales staff. So just when we said 1 data point increase, it means completely different things based on which variable you're talking about. So, so that's the reason, like I was saying, like you can't compare based on those like the value of the coefficient among the variables. But at the end of the day, we still want to know, compare which, we want to know like which variables have more effect, more important. That's what we're trying to do, sort of like subconsciously, right? So there are a couple ways to do it, and I want to introduce two things. One is a standardized variables. Standardizing or normalizing the variable values, then basically we can kind of like have all the variables values to be in a similar unit, right? So by using standard deviation, right? Because that takes account for each variable variance, and then get like sort of like average variance difference from the mean. So therefore, even though year or monthly income or job level, all the different variables with a different variance can be standardized, right? So like then we can actually use those as a predictor variables, and then we can compare. The other one is a relative importance with Rsquare. Let's start with a standardized variable. To do so, what I was saying is basically here the problem is when you go to summary view, age is from 18 to 60, and distance from home is 1 to 29, and then like education is like 1 to 5. So there's a different variance. We can actually standardize these to have similar variance. Like how you do it? So here, basically, like there are two ways to do it. You can just basically what we want to do is normalize this, let's say like age. To do from column header menu, like you go with work with a numeric function, and there is a normalize function here. But you can do one by one, but as you know, there are a bunch of numeric variables, and you just don't want to do like one by one. The two ways to do it, like you can select like multiple variables, and then you can start from here and then work with the numeric function. Or you can click on this like plus button at the top right hand side, and then select this mutate bracket create calculation for multiple columns. Either way, we'll do the same thing. So let's select this one. And then you can select the columns, how you want to select that. You can go one by one, but again, it's much easier. There's a much easier way to do it, which is to match with column data type. And then what's the data type? Well, like we want to do like numeric. And then calculation type, the convert data type and so on. Like what we want to do is work with numeric function and then select normalize. And then what this is going to do is like apply this normalize function to all the columns as long as they are numeric data type. Let's do it. Click on run button, and then like all the variables, numerical variables, being just standardized or normalized. And when you go to summary view, I think it's all the stuff is basically like standard deviation 1 and standard deviation 1. Most of all the stuff is becomes a standard deviation 1 now. And then with this, now that like all the variables have the same variance, then we can use this one. So like I'm gonna just copy this analytics and duplicate. And this one, I call it standardized variable. And then I'm going to move this to pin, because right now the pin is pointing to the step before standardizing these numbers. So like I'm going to move this because that's the these new variables are the one like I want to use to build upon it. And all I need to do is just click run button, because I don't have to reselect the variables because those are all selected. But the values inside those variables are now different and converted. So I'm going to just click run button. Then like I get something like this. So now it's more appropriate comparing between next to each other. So like for example, now the total working years is now it's like a coefficient 0.07. Value is small because probably the most effect the changes of monthly income is coming from job level or maybe a job role, but still here. And compared to what we used to have was like a total working years super close to zero compared to other variables. So it was kind of hard to see. But now here is standardized. So this view gives you more sort of reasonable way to compare among the variables. Okay, so that's a standardizing way to do it. But there might be some problem, might not be appropriate always because the variance might vary among the variables and the underlying distribution vary among the variables. So we are sort of like, if these are all normal distribution, these things are super easy. But in the real life, it's very rare to have all the variables be normal distribution. There are a bunch of different types of variables. I don't know, like a bunch of, but the various type of the distribution. And also, like I think here is well, so with the different variation of the different variable, we won't give you the sort of same unit with the standardized numbers, and so like there might be some kind of bias in that data. So like I'm not an academic, so like I think this just by standardizing these numbers, it's already give me enough information, but might not be sometimes might not work perfectly in some cases. But here's the third one. To me, is sometimes there's a little problem because how to interpret when categorical variables are in the mix. When categorical variables or you compare with the baseline. So for example, job role, like you comparing against sales executive to, for example, manager, right? So then what is the effect of job role? Because the job role, each value of the job role becomes the variable here by, sort of like a one hot encoding kind of transformation happen behind the scene as part of this linear regression algorithm. So like we don't know like if job role is more important than the job level or not by just looking at this. So like it's standardizing numerical variables. If you have only numerical variables as the predictors, it's much easier. But then the moment you categorical comes in, it kind of get harder. So another way is a relative importance with Rsquare. So what's the relative importance? So like that is when you go to this like importance tab, and when you click on this, and then you get this chart with error bar. But this job level, for example, is the highest height of this bar, which means the highest, most important compared to others. And it looks like the first four, like a job level, job role, total working as age, these four seems to be more important. And how we are getting these numbers, like when we say it's like important 0.34, what that means. First of all, this is more to do with the kind of relative importance. So compared to next one or other variables and how much more important, that's the kind of information we're getting here. But there are a couple ways to get these numbers. When you click on the property, there's a variable importance section. And then you can disable it too, but default is true. The method, there are a couple methods. The first variable, last variable, and the Lindemann, Melander, and Gold variable. Method. And what are those? I'm gonna just quickly explain this. It's all about R-square. So like it's basically talking about like how each variable contribute R-square. And R-square is the measure of how much a given a variable or given set of variables explain the variance of the target variable, right? So when you compare to mean, so like here's a red line, the mean, this is a kind of revisit like we talked about in the previous session. And if you want to know more detail, check out the previous session. But it's about like the difference between the actual value and the mean, that's the variance, and how much of the variance being explained by this prediction model, or in this case, a linear regression model, which is the purple line. And what that means, it's very simplified word. We have like this number of employee, we draw the linear regression line, and then there's a difference from the mean to the green person, that's the actual number. And then the model thinks this person should be making this much on the blue line. And that is explains 60% of the variance of the monthly income. And then not just one, is we combine all of these and then I get the average numbers. But that's the R square in a nutshell. So having said that, now that we have the variable, three options. First variable method is a very simple one. Basically, like behind the scene, it builds a model for each variable by using only one variable as a predictor. And then like you get, so let's say like ABC is the name of the variable, ABC, right? And then like you build a model and then you get the R square. Then basically we're comparing those numbers. So basically what we're looking at in the exploratory, the variable importance chart are these numbers. You can change the setting method to last variable, for example. Last variable is that like basically like base model, which is you build a base model, which is to include all the variables, and then that's in this case, let's say like 0.9 as R square or something. We calculate that, and then without a given variable or interested variable, let's say like A, so without A, that means B plus C, and then you get the R square, which is happen to be 0.1. That means the difference between 0.9 and 0.1 is the contribution of the variable A towards the R square. And do the same thing for like each variable, and then you get the sort of like a contribution R square numbers. Then like based on that, like we can talk about a relative importance. The last one here is in the world though, like, other methods too, but like here only like 3 in exploratory. But anyway, so here is it's more complicated, and I don't recommend because this is going to take a lot of time. So if you have like only a few variables, that's fine. But when you have like a bunch of variables, let's say 10 or 20 included, and then it's going to take a lot of time. So like you might want to just go have a big lunch or something. But anyway, to calculate this, basically like you, let's say like we're interested in A. And then what's going to happen is like it creates the model for every single possible pairs as it can. So like it's just A and build a model on A plus B or A plus C or A plus B plus C and so on. And then you build a model without A. And then for example, B plus A is a model. And then like you build B as a model. And then find a difference. And then let's get maybe like difference is R square. And then how much, in this case, the R square number is that we can consider is coming from A. And then like we have a bunch of different numbers, and then we average out. So that's the Lindemann-Melenda-Gold method. Again, this takes a lot of time because it goes like every single combination. As the more variable you add, it takes more longer time. Anyway, and then at the end of the day, like based on my experience, a small experience, but I don't see much of a difference. So like if you want to go into the very, very precise things, and then you might want to try, but usually the first variable or the last variable is good enough. So now that we know those 4 variables seems to be important. So can we just go with those 4 variables? So what that means here, this job level, job role, total working years, age, these 4 are sort of like much bigger than the other 4 variables. So how about changing this so let's say I'm going to create, I'm going to just copy it and then change the predictor variables to be just age and job level, job role, and then like working years, only 4. And then build a model again. And then like let's see the coefficient here. And then like we get this view. And it seems like age is not even like significant. It seems like a p-value 0.46, so might not have much of the effect, the true effect. But here is one thing. Like when we go to summary view, and then like we can see like R square. R square is again is how much this model can explain of the variable variance of the monthly income. And then when you go back to the original one, that one like with all the variables, and go to the summary, is this R square 0.94, and then like this one is like 0.943, it's kind of hard to compare these two numbers going back and forth. So I just took the screenshot of this. Okay, and then and compare these two. So the above the top is the one that model with all variables, and then the bottom is the one that I selected only for variables. So like I excluded all the other variables, and then just purely compare the R square. And R square decrease, right? Just a little bit, like 0.001 or something, just a little bit decrease. So that means these four variables lost some kind of explainability. But this is actually expected. And the reason expected is that R squared tend to increase, or almost like all the time, always increase when you add a variable, regardless that variable has any meaning or not, or has any true effect or not. So there is an adjusted R squares being created, and then this one does give the penalty when you add the extra variable as a predictor variable. So in order for this number to increase, the variable, a given variable, needs to have some kind of impact effect on the, in this case, monthly income. So when we look at this adjusted R square, adjusted R square increase with only 4 variables, meaning all the other variables are not contributing to this model. That's why the adjusted R square decrease with all variables, which is the top one. So that means we don't really need those variables in this case. We didn't really lose much of the explainability by selecting only these 4 variables. So the more detailed explanations here, but I think I already talked about it. So I'm gonna skip these 2 slides. And then, so now that we are, and there are other measures like AIC and so on, but I'm gonna just talk about only, I just talk about R square and adjusted R square, and when you wanna use and what are these. And then last topic of today is building multiple linear regression models. So far, like we basically ended up with these 4 variables in terms of, in order to explain the changes in monthly income, right? So now here are the questions. Do these variables have similar effect on monthly income for all the job roles, the category, right? It's like a sales executive or an HR or research director and so on. But all those job roles have similar effect in terms of like, let's say like working years effect or job level effect. And if there are, then those effects are significant for all the job roles. Maybe like some job role, like let's say like research director. In the research director, like working years is more important, but maybe like sales rep, maybe like working years don't really matter in terms of like monthly income. And which job roles can be explained by these 4 variables better compared to others. Maybe like sales executive, we have a good model here, but in order to explain the sales rep, maybe these 4 variables don't really help. And then those are the things like we want to understand. So that means we can actually create multiple models. In this case, multiple linear regression models. It's kind of like a weird way to say, but basically creating multiple models. And in Exploratory, you can use a repeat by. And how you, and the repeat by is here. And how you do, what's happening is behind the scene, when you click the run button, based on the data, it builds the model, in this case, a linear regression model. By using repeat by, it splits the data into each group of the category of the whatever the variable you selected for the repeat by. So let's say that we selected the job roles, then that means you're gonna have the, it will create the data for just HR, and then filter the data only for the research director and so on. And then given that each data, and then it builds the model. So like we ended up like how many number of the models as much as the original value, unique values of each variable. In this case, job role has 9 categories. That means you're gonna end up like having 9 models being built behind the scene. Then we can start answering these questions. So let's take a look here. So we have, I'm gonna go with without standardizing those variables because it's easier to understand the numbers with the raw number compared to standardized numbers. But what I want to do is first select only age and then working years. Maybe like age doesn't really matter, but I'm going to just select it anyway, and the job level. And I don't want to select the job role. Why? Because I want to use this job role to be the repeat by column. So I'm going to just go with this only 3 variables as a predictor. Then select the job role as a repeat by, and just click run button. That's it. That's all it takes. And then like, you ended up getting the model for each job role. Okay. And then I'm going to just click on this chart property and then do like a 5 columns in row, like 5 charts in row. And then I'm going to hide the right hand side here to make it easier to see. Okay, here. So like we have like a 9 model or like a 9 chart in this case. And then like we can see, for example, healthcare representative. And like we can see like a job level, one job level increase will have can expect about $3,000 increase in the monthly income. And then compared to, for example, research scientist or even like sales representative, it's like one job level increase, you can expect only like $899. It's like a $900 increase. So they're different how much of the increase you can expect among or in each job role. And another thing is that here, when we see like total working years, like some of the job roles, total working years doesn't matter, or we don't have enough evidence to say that total working years make difference here. You know, can be because we have only 1,400 record employee. So like maybe because of that, we don't have enough data in the human resource and research director or something. But at this point, with this data, we don't have enough evidence that total working years have any effect on monthly income. But healthcare and then or manager or manufacturing director, these have some sort of effect on the monthly income. And then we can quickly see like what does this mean. So for example, we can see the scatter plot, and then let's say like a total working years. Where is it here? The monthly income. We can see that the relationship between these two by the group, right? And then like let's say job role, and then like we have this type of different role view. And I'm going to change that to this one too, also 5 columns. And then like I can draw the trend line and linear regression line here. And then it's just some, for example, manager is almost like a total working years increase. Ooh, I think I'm going to do this with this without standardizing numbers. Okay. And here. Yeah. So the manager is like a 1 year increase or like and monthly income is kind of like going up. But some of the job maybe not really matter much. But this is again, this is like simple linear regression. The thing we are looking at here is not just total working years, but also account for the job level change. So without the job level change, this much is still like the total working years still has some effect on monthly income. But human resource, without the job level, then the total working years, we don't have enough evidence that total working years have any effect. So we can see some difference among each category, in this case, the job role. And then last, not the least, is that like, so we get this model. It's a very simple model. It's like age and job level, total working years, and how much these 3 variables can explain the variance of the monthly income for each job role. Some job role might be easier to explain by using these 3 variables. Some might not, and that's something that you can go to summary. And then here's the Rsquared. This is the one that you want to look at. And then like you can click on Rsquare, and then research director. We can explain the variance of monthly income by using age, job level, total working years. While sales rep, we can explain only 30% of the variance of the monthly income by using age, job level, and total working years. You can see like what that really means by going to this prediction tab. A prediction tab is like x-axis the predicted values and y-axis the actual values. And then this line is basically kind of a diagonal. So like if all the blue dots are the actual values, right? Think of it like each employee. And if all those blue dots are on this gray, like this line, then that means it's a perfectly like model. It's like an actual value, the predicted value that identical. But you know, in the real case, it cannot happen, right? So because nothing can be linear. So here, like we can see, for example, some of the stuff, the sales rep, it's almost like the line is kind of like the slope of the line is kind of like almost like a flat here. And then it's because this data, like blue dots, and it's almost like there's no sort of like linearity. So therefore, it's having a hard time, like sort of like draw the line in this thing. So this is why this model are not really good at explaining. So think of it, this basically is based on sort of like the calculated R-square. So like because all the variables compared to maybe like let's say like average lines, like let's say 3,000 or whatever, and then you know looks like all the variants are not being explained well, but for the sales rep. Where research director, which one was that? Let me see here. Yeah, research director in this case here seems like it's this model is explaining well because all the blue dots and then like this like this gray line seems to be closer compared to others. So that's one way to understand why this R-squared is different. But by looking at here, the point is that like some of the group can be explained easier than others. And I think that's really the point. Okay. So with that, I think today that's it. So if you have any question, please ask. I'm gonna stop sharing the screen here, and then here we go. Okay, so with that, if you have any question, I think probably muted. So if you have a question, you can unmute and then you can speak, or there's a chat window, so you can throw whatever the message in the chat window as well. I'm gonna wait for like just 30 seconds, and then let's see.
I have a question.
Oh, hi, Dan.
Hi.
We will shortly be arriving.
Not great reception, so I apologize for the background noise. My question is, does the adjusted R-squared take care of the fact when you're doing multiple models that you're kind of including another variable by having lots of models? Doesn't that mean that the R-squared is going to be an overestimate if you're building models to specific data? So you're kind of adding another variable on the side.
So it's would you repeat that question, please?
So I'm kind of new to mixed effects. I've been started